No questions? Okay. So here are some common architectures in neural network. You have perceptron, CNN, RNN, transformers, autoencoders, and GANs. So what we have been tackling all this time is the perceptron variation of neural networks. This is the vanilla neural network. I don't actually expect you to use the other architectures in this class. If ever you're gonna use neural networks, I still suggest using the more traditional models if you can, because they're more interpretable. But if you wish to use neural networks, then that's fine. But there's gonna be lots of complications. This is not a deep learning class, so I understand if you can't really implement it properly. And we're just allotting one session for neural networks, so that's okay. But yeah, this is the vanilla neural network, the perception. We also have CNN. We use this architecture for image data. Use this for object detection, computer vision, real-time object detection, that stuff, image classification. It is called convolutional neural network because of the convolutional layer that you're adding. So what happens there is it's like a moving window. You try to segment your input image into many blocks, and then you try to generalize using this convolutional layer. That's what's happening in a nutshell. You keep on doing that, the convolutional layer and the pooling layer, until you just use a dense layer at the end. This is just you're just basically making it flat, and then fully connected layer to the out of class. So yeah, the convolutional layer is what's added here. You also have recurrent neural networks, or RNN, good for sequential data. You basically just look at the previous inputs that you have. That's why it's called recurrent. You look at the previous values. You look at the history to make a prediction. Transformer. Okay, so recently, this is the architecture that is being used a lot. It can be used for so many cases. It is good for sequential data. It essentially replaced RNNs. So this is like a good GIF that I found in the internet that shows what's happening more or less in transformers. So think of them as your nodes. This is your input, just variant. This is French, and then it is converted to English. So it pays attention to different nodes, similar to what's happening in your vanilla neural network, but it makes use of the, what do you call that? There's a term for that. The attention mechanism. It is inspired by a previous paper from Google. There's attention. Wait, I'm trying to remember the name of the paper. There's something attention in it. Attention is all you need. A very influential paper in the field of deep learning. So that is the start of the transformer architecture. And yeah, lots of use cases for transformer. The recent GPT models, the ones that you see that could generate paragraphs that seem that they're made by humans. It's transformers. It was originally made for NLP, but it's also being used in computer vision now. But yeah, it was originally an NLP model. Autoencoder. Okay, so autoencoder is generally used for dimensionality reduction. So you have your input and then your output. The idea is to compress it, and then you're hoping that the compression could eventually be decoded once again. So there's encoder, decoder. You're trying to simplify your input. Maybe you have, like, say, an input that has 1,000,000 features, just for example, and then you just want to represent it using like 256 neurons, from 1,000,000 to 256. But anyway, given that 256, can you recreate that? Of course, it's not going to be exactly the same as the input, but we're hoping that it's going to be more or less similar to that. So you could use it for dimensionality reduction in that sense, because this is a good enough representation of your original input. Even though what you're going to get in the output is not exactly the same, it should be good enough. So that's autoencoders. GANs. For GANs, you use this for generating images. This person does not exist, uses GANs. So you have generators and discriminators here. And what's happening is you have two models, the generator and discriminator, and they're sort of trying to fight each other. The generator is trying to fool the discriminator. The goal eventually is to create an image that looks very, very real, and then the discriminator is getting better at its job to identify if this is real or not. In this example, so the detective, that is the discriminator, and then it's trying to differentiate the real input versus the one that is generated by the forger, the generator model. You end up with a very good model that can create images that seem real. So that's the output of this network. I think that's it. Oh yeah, that is it. Any questions? That's neural network or deep learning at a high level. There are so many nuances to deep learning. It's a big field on its own, by the way. And this is just the simplification of that. In the next session, we can do the notebook for that.